Topic 2.5 is about Lewis diagrams. So the objective for this topic is pretty straightforward. Represent a molecule with a Lewis diagram. So we're going to go through some of the rules and then we are going to look at an example. So reminder, Lewis diagrams are a drawing or a picture that represents the bonding in a compound. So when we draw Lewis diagrams, and here we are we're mostly going to be talking about covalent compounds, but no matter what, we're going to follow the octet rule. So the octet rule tells us that atoms will gain, lose, or share electrons to achieve 8 valence electrons. 8 is our magic number, hence the octet rule. So ionic compounds will gain or lose electrons. So that's where they're going to be transferred from the metal ion to the nonmetal ion. So the nonmetal is going to gain the electrons to reach 8 in its valence. The metal ion is going to lose any of its valence electrons, so its valence then drops down and has a complete 8 below that. In an ionic or in a covalent compound, they're going to share electrons to achieve 8. And so we use Lewis diagrams to show how those electrons are being shared and how that bonding actually occurs. So remember that this is just a drawing representing the bonding. We use these as pretty much the standard way to represent covalent molecules. However, they do not show exactly what's going on. And we're going to look at some of that in a later topic. But this is just a representation. It's not actually what's happening, but it's a pretty darn good representation. So a couple of things, some terminology about Lewis diagrams. These pictures are taken from your textbook. I can't remember exactly what page or which diagram, but if you look up drawing Lewis diagrams in your textbook, you should be able to find these pictures. So some terminology, we're going to start with the hydrogen, so the H2. So there's electrons get shared, so we say that they're an electron pair in a bond. When we draw the Lewis structure, we draw them with a single line. Okay, so that's showing hydrogen. Hydrogen on its own has 1 valence electron. When you have 2 hydrogens together, they share those 2 electrons, they form a shared bond. Hydrogen is one of our exceptions to the octet rule. Hydrogen only shares 2 electrons, so it's only ever going to form 1 bond. If we move across the slide, if we look at fluorine, so fluorine normally has 7 valence electrons. Okay, so if you have 2 fluorines together, they're going to share that lone valence electron, that 7th valence electron, to form a shared pair, which then when we draw the Lewis structure, we show it with a single line because it's a shared or a bonding electron pair. The remaining electrons are drawn as dots, and those are called lone pairs of electrons. Now, sometimes in order to reach the octet, atoms have to form double or triple bonds. And so in that case, they're shown with 2 lines if it's a double bond, 3 lines if it's a triple bond. Each line representing 2 shared electrons or 1 shared pair. Dots are still representing lone pairs or unbonded electrons. So in CO2, we have our carbon in the middle, our 2 oxygens on the outside. In order to get the octet around carbon, each oxygen has to share some electrons with carbon, so it forms a double bond on each side. And then our triple bond example is nitrogen. So just like with the double bond, we're using 3 lines instead of 1 or 2 to show triple. Each line represents 2 shared electrons or a shared pair of electrons. So there's 6 total electrons being shared between the 2 nitrogens, and then a lone pair on each of the nitrogens. So let's go through the steps for how to draw these structures. Okay, so general steps. Again, this example comes from your textbook, so you can find these examples, but it was a good, clear way for me to put it up on the screen for you. I am going to go over several other examples in the specific examples video for this unit. So if you need additional worked through examples, I will be doing some of those in a separate video. So your first step is to determine the central atom. And it's usually the element that has the lowest electron affinity, and it's oftentimes the first one listed in a chemical formula, unless hydrogen is listed first. Hydrogen will never be your central atom because it's only going to ever form 1 bond. Otherwise, more often than not, it is the first element in your chemical formula that's going to be your central atom because that's usually the one that has the lowest electron affinity. So then once you determine that, you're going to want to count up the total number of valence electrons. So you're going to look at your periodic table. It's based on what column it's in, and you're going to count them all up. I like to think of it as each element is bringing a certain amount of valence electrons to this bonding party. So you got to figure out how many you have total. So in this example, we have a carbon, a hydrogen, and 3 chlorines. So carbon is always going to bring 4 valence electrons. Hydrogen will bring 1. Each chlorine is going to bring 3. So, we have 3 chlorines, each chlorine brings 7. So 7 times 3 gets us 21. Okay, so then when we get 21 electrons from the chlorines, 1 from hydrogen, 4 from carbon, which gets us 26 electrons total. So once you have your central atom, you're going to arrange the other atoms around it, and you're going to connect them to the central atom with a single bond. So carbon's our central atom. We're going to put our 3 chlorines and our hydrogen. It really doesn't matter where they go. We're not going to worry about stereochemistry or arrangement, so in whatever order you want, but each one is going to be surrounded. We tend to draw Lewis structures in a nice, neat, orderly way, so they tend to kind of form crosses or diamond shapes, just because it makes things nice and neat. We'll talk about actual shapes later when we talk about VSEPR theory. So we connect each of our outer atoms to our central atom. Sometimes they're called terminal to the central atom with a single bond. Each single bond represents 4. So each single bond represents 2 electrons. So we have 4 pairs of electrons. So in this picture so far, in this representation, we started with 26. We've used 2, 4, 6, 8 electrons, 2 from each bond. And so that tells us how many we have left. So then you're going to take whatever electrons you have left and you're going to place them as lone pairs around the outer atoms or the terminal atoms so that everybody has 8. Remember, hydrogen is not ever going to have any lone pairs because hydrogen only wants 2. So it's just going to make 1 single bond and that's it. So we have our remaining electrons and we place them in as lone pairs around each of our chlorines, and that uses up all of our electrons. So if you were to go count them up, we have 2, 4, 6, 8 in our bonds, 2, 4, 6 around each chlorine, and so that gets us to our 26 total valence electrons. So we don't have any left, everybody has 8, and so we don't need to do anything else, and this is the end of our Lewis structure. So again, in my example video, I'm going to go through some other examples where you might need to form double or triple bonds, and kind of some of those more oddball type examples, but these general rules apply, and then it's when you get to the last one you have to kind of make some decisions about, do I need to form double or triple bonds in order for everybody to get 8 valence electrons. So that is how you draw Lewis diagrams for covalent molecules.